looking at an RLC circuit, except it has a different topology than what you've seen before. So now we have a resistor in series with L and a resistor in parallel with C. So let's look at how to derive our common expressions that we've been using for RL and C, which will help solve for any solution for this problem. So what is VC of t and IL of t? So our first step is to use KVL and KCL to describe this circuit. So our first KVL equation is going to be this outer loop. So starting from this bottom node here, we have, and traveling clockwise, we enter negative Vs. And then we hit our first resistor, and it has a current of IL through it. So R1 times IL is the voltage drop here. And then we need the voltage across the inductor. So the voltage across the inductor is equal to L times the current, or times the derivative of the current going through it. So L dIL dt. And finally, the voltage across the capacitor, or across even R2, is just Vc. So the sum of these voltages is equal to 0. That's our first equation. Our second equation is a KCL at this node here. And this will relate, again, IL and Vc together. So what's the current entering through the top branch? The top branch has a current of IL. And then the bottom branch, what's the current through a capacitor? Well, that's just the capacitance times the derivative of the voltage across it, plus, so that's the current through the bottom branch. And then we have another current entering R2, and the current entering R2 is Vc, the voltage across it, across the resistor, divided by R2. So we have two equations and two unknowns, and both of these are differential equations, and they're coupled together. So now we want to substitute in the KCL equation into the KVL to get a second order differential equation, which we can solve. So now we're going to combine our two equations together. We're going to substitute IL into the first equation. So we start off with negative Vs plus R1, and we're substituting IL, so that's C dVc dt plus Vc over R2 plus L times ddt. And now, in this case, we are substituting in, again, IL, and then we'll take the derivative later. And finally, we have our plus Vc, and all of that equals 0. We can, so now let's kind of expand and see where this takes us. So we have negative Vs plus, we're going to distribute R1, so we have R1C dVc dt plus R1 over R2 Vc plus LC. Well, here we have a derivative, and it's being distributed across this IL equation. So here we have an L. This C is not varying in time, so the derivative, the derivative of C isn't going to change it. So we can pull it out front. And then we have the derivative of Vc. And so we have a second order here, second order derivative of Vc. And then we have kind of the same process. We can pull out R2 for the second term and take the derivative of Vc, which is just a single derivative here, plus Vc equals 0. So now we can kind of group terms together and put it into a common form. So the common form is to have our second derivative in front, and then group our first derivative together, and then group our constant term together, and have that equal our second term. So let's fill in these spots. So we have R1 times C, except that's being divided by this constant LC, so we have R1 over L. plus we have this dVc over here, and so dividing by LC, we have 1 over R2 times C. And finally, for VC, we have a R1 over R2 plus 1. And then our forcing function is Vs over Lc. So now this kind of looks like the second order differential equation we've seen, where we have d squared y over dt squared plus 2 alpha dy dt plus omega naught squared y equal to k. So our alpha is 1/2 of R1 over L plus 1 over R2C. Our omega naught squared term, or omega naught, is the square root, oops, sorry, there's a L over C there, is the square root of R1 over R2 plus 1 over LC. And our K is Vs over Lc. So now we can use all of our previous solutions for underdamped, overdamped, and critically damped by plugging in our respective R1, L, C, and R2 into these formulas and use the exact same solutions that we've seen previously. And now you can solve the same or create new differential equations for any topology of L's and C's.